we're going to start to move into actually graphing quadratic equations versus just sketching them, where we want the points on the graph to be accurate and specific versus just like a freehand sketch. So we're going to use the power of symmetry to help us do that. So it's important to know that a parabola is symmetrical. There's always going to be that vertical line, which we call the axis of symmetry. And so the vertex will always kind of be in the middle of that. And then each point on either side, for example, like this blue point would be symmetrical to that blue point, and then like this green point and this green point, and so on and so forth. And so the reason that's going to be helpful is because what you could do is you could just graph one half of the parabola, and that will allow you to get the other half. But in order to do that, you have to have the center first, which is always going to be your vertex. So for right now, we're going to see these equations in vertex form, which is here, that y equals, remember, a can be positive or negative, x minus h squared, and then plus k. And that's going to allow us to find our vertex, because our vertex is always going to be the hk point. And so in this case, my hk is going to be 3, 1. And so I've got my table here, and in the center of the table, I've got that vertex 3, 1. And so I'm going to build around that. And so you kind of want to picture like that being here. And in a minute, we'll graph it on this. So then from 3, 1, you want to go 1 to the right on the graph, if you could, which would be like a point of 4, and then 1 to the left. So let's kind of start to see what this is going to look like, just to kind of give you an idea of why we're choosing points like this. So I'm going to actually look at this. So I can see that my parabola, because my a value is positive 2, my parabola is going to be an upward facing parabola, and it's going to be pretty skinny or narrow, which means it's going to grow pretty quickly. So I want to have room for an upward facing parabola that has a vertex of 3, 1. And so let's see, I'm going to put my x and y axis down here. Oh, I thought it was a notability. I thought it was going to do that straight line for me. Okay, so I'm going to graph my vertex of 3, 1, and that's here. And so I can see, like, for example, if I just do a super quick sketch, I know my parabola is going to look something like this. But I don't want to do a sketch anymore. I want to make it accurate. And so that means everything on this side of my vertex is going to be symmetrical to everything on the left side of my vertex. So for example, if I were to go one space to the right, I'm now at an x value of 1, 2, 3, 4. That's going to be symmetrical to an x value of 1, 2. Same way that these two blue points are going to be symmetrical. So that's why here on this table, if I start with my vertex, my next x value is 4, and then 2. And so then I can go 1, 2 spaces away from my vertex, and so this is at an x value of 5, which means it's going to be symmetrical if I go 1, 2 spaces to the left, which is going to be an x value of 1. So I'm building outward from the middle of my parabola, which is my vertex. So 4 and 2 are going to be symmetry points here, just highlighting them to show that. And then 5 and 1 are also going to be symmetry points, which means they're going to have the same, so 4 and 2 are going to have the same y value, 1 and 5 are going to have the same y value. If you can kind of see that, this is just like an example over here. So symmetry points, they're the same height. The reason that's going to be really useful is because in this quadratic equation, I don't have to replace x with both 4 and 2. I only have to choose one of them to do. And so I could do 2 minus 3 or 4 minus 3. I'm actually going to do 4 minus 3 because I know that's going to keep everything positive, and that's my preference. So I'm going to do y equals 2 times 4 minus 3 squared plus 1. So all I've done so far is I've taken this x value of 4 and I've put it in the place where x is. And now I'm trying to find what y equals when x equals 4. This is very similar to what we did last night on our homework. And I'm going to follow PEMDAS to do that. So I'm going to start by doing 4 minus 3, which is 1. And then 1 squared is 1. Times 2 would be 2. And then plus 1 would be 3. So that means that when I replaced x with 4 in this quadratic equation, the y value equaled 3. Why is that important? That means that if I were to go and also replace x with 2, it would also have a y value of 3 because they're symmetry points. And so now I can go over here and graph these on my graph. And so I can go to 4, 3 and 2, 3. And so far it's good news because I can see that if I were to connect these, my parabola would be facing upward and it would be narrower than my parent function, which was my expectation based on this a value. So my next symmetry points are going to be 1 and 5, and so that means that they'll have the same outputs regardless of which x value I use. So again, I'm going to choose to use 5 just because that will keep it positive, and so I'll do that over here. So y equals, I should probably do this in green since that's the color, y equals 2 times 5 minus 3 squared plus 1. So all I've done so far is I've taken x and I've replaced it with 5. And now I'm going to follow PEMDAS in order to solve or evaluate this. So 5 minus 3 is 2, which is getting squared. And so my next step would be to square 2, because I've got to do exponents before multiplication. So that would be 2 times 4, and then plus 1, which is 8 plus 1, which would give me an output of 9. So I replaced x with 5, and I got a y value of 9. And since it's a symmetry point when x is 1, that also means that my x value, or my y value, would be 9 when x equals 1. And so now I can come over here and graph that. So the first point that I'm graphing is 5, 9. And then I'm also graphing 1, 9. And that would be enough to graph my parabola. We just added one extra to this table, which was the x-intercept. The y-intercept is always going to be on the y-axis, and it will have an x value of 0. And so that just means to change x to 0 to see what y would equal. And so I could do y equals 2 times, I'm going to do this part, 0 minus 3 is negative 3, which is getting squared, and then plus 1. And so square negative 3 would mean to do negative 3 times negative 3, which is positive 9, and then plus 1. And so then I would get 18 plus 1, which is 19. So we'll see if I have enough room for this. I think I do. So I had purposely put my origin kind of down here, knowing that it was going to be an upward-facing, quickly growing parabola. So I think I've put this correctly. And then the other thing I could do is, even though I don't have this point in my table, I know that this y-intercept would also have a symmetry point over here. And so I can go over one right of that green point, and I can add that symmetry point there. And so now I'm ready to connect. As best I can, I'm doing it with swooping motions. It's a little harder when they're farther apart. And my parabola would look like that, which again matches my expectations of an upward-facing, narrower parabola. And then it's asking for the axis of symmetry in the vertex, so I've got my vertex here, which is where all that symmetry is happening. And then my axis of symmetry would be this vertical line right here that cuts that parabola down the middle. And if you were to fold, if you could picture yourself folding your paper on this line, then the two halves of my parabola would line up perfectly with each other. And that axis of symmetry equation is going to be x equals 3, because this line right here represents the line where x always is equal to 3. And my vertex again was the point 3, 1. So in this example, I'm just going to get you started with your vertex. And so again, our vertex, when we're in vertex form, which is what it's being written in, is going to be that point hk. And so in this case, my h value is actually negative 5 because it's plus 5, and my k value is negative 2. And so that means that my vertex is negative 5, negative 2. And so when you create your table, you want to build around here. So think on the graph, if you're at negative 5 on the x-axis, what's equidistant on either side? That would be the points negative 4 and negative 6. And then one more equidistant would be negative 7 and negative 3. And then your y-intercept, like we said, always occurs when x is 0, and it may or may not fit on this graph. We'll see, but we can still fill it in the table. So I would start by filling in this table by replacing x with one of the blue points, because they're symmetry points, and they'll have the same y value, and with one of the green points, because they'll have the same y value, and then again with 0. And then once you kind of see what your table tells you, although your expectation should be that it's going to point down because it's negative and it's going to be the same size, that can help you place your axes on here to make sure that your parabola fits. Let's go ahead to number 3 to get started on that one. So on number 3, I'm going to start by identifying my vertex, which is going to be HK. And so my vertex in this case is going to be 4, because that's my H value, and then there's nothing being added, so that's going to be a 0. So my vertex is 4, 0. And so then my symmetry points from there would be 3 and 5, and 2 and 6. And then my y-intercept, if I am able to put that, would be 0. Now before I graph this too, I also want to think about some expectations that I have for my parabola to make sure when I see it on the graph that it matches my expectations. So some expectations that I have are that it's going to be wider than the parent function because of the 1/2. It's also going to be an upward facing parabola, so I want to make sure that happens when I do that. So now I'm ready to replace one of each of my symmetry points in my equation. And so I'm just kind of looking ahead and thinking, okay, 3 and 5, I could use either of those. 3 minus 4, 5 minus 4. I'd rather do 5 minus 4 because it's positive. But then I'm thinking here, like, okay, that's 1. 5 minus 4 is 1. 1 squared is 1, and then I have to cut 1 in half. And it's not too bad. But if possible, I would rather avoid fractions altogether. And so something that I could do, if I could keep these symmetry points as well, or symmetry points are symmetry points as long as they're equidistant from the vertex. So 3 is 1 space away from 4, and 5 is 1 space away from 4. That's why they're symmetry points. 2 and 4 are 2 spaces away. 4 and 6 are 2 spaces away. That's why they're symmetry points. But what I could do is I could also use different symmetry points, as long as they're equidistant, that are not going to give me fractions. And so, for example, I could have jumped from 4 to 6, because 6 minus 4 is 2. 2 squared will always be even, and then I can easily cut something that's even in half. And since 6 is 2 spaces away from 4, I want to go 2 spaces away the other side, which would be 2. And then I want to choose another number that if I were to subtract from 4 would give me something even, so if I square it, it's even, I can cut it in half. So I might jump to, say, 8. And so now 4 and 8 are 4 spaces away, and then that would go to 4 and 0, which would be 4 spaces away, which will also happen to be, if I choose to go that path, that would be my y-intercept. So it's kind of up to you which points you want to choose to graph this. You could choose 4, 5, 6, 4, 3, 2, or in this case, again, I might choose, I'm picking numbers specifically that I know are going to work out nicely with the 1/2. It's totally up to you. Regardless of how you choose it, you're going to replace x with only one of your 2 symmetry points for each color. And then when you graph it, just make sure that you place your axes in a way that will allow your parabola to fit on the graph, and it would look the same regardless of if our tables are a little bit different. We should have the same parabola when you're done. So go ahead and finish this one up as well. Number 4 is a graph just to take a look at. And on this case, we just kind of want you to see, like, okay, we've got our vertex of 2, -4, that's here. Here's an axis of symmetry. And then one area that we're going to begin to focus pretty soon is on these x-intercepts as well.